Hello, everyone. Welcome to the Audio Precision webinar. Today, we'll be discussing ADC and DAC testing with Daniel Knighton, who will be leading the conversation and providing demonstrations in APX 500 software. My name is Paige Morford, and as the producer of the event, I would like to go over a couple housekeeping items before we get started. So please note that this session is being recorded. And secondly, we welcome questions during the webinar. If you have a question for Daniel, you'll see on the right side of your screen either a window or a chat icon in the top right-hand corner where you can submit your question via the Microsoft Teams function. If you prefer, we will also be having formal Q&A at the end as well. So without further ado, Daniel, I turn it over to you and the floor is yours.
All right, thank you, Paige. So my name's Dan. What we'll go through in the next hour or so is, I'll say, the basics of testing digital to analog and analog to digital converters. We'll talk a little bit about the physical input and output configuration of the analyzer in relationship to the device we're testing. And today we're basically going to look at the two canonical classes for DACs and ADCs, SPDIF and our digital serial interface. We'll have a little bit of discussion about units of measurement when we're talking about digital audio. And I hope we'll spend most of our time looking at measurements on these devices themselves. As Paige said, feel free to submit any questions you may have as we go via chat, and we'll also have an opportunity at the end to review and go over any questions. So first of all, who am I? So I'm Daniel Knighton. I started working at Audio Precision in 2000. I'm currently the general manager of the Audio Precision product line. We recently joined with Grass Sound and Vibration, so that's why I say the general manager of the Audio Precision product line. I have a counterpart within Grass as well. Today's demonstrations will be using the APX 555B analyzer. I'll talk a little bit about why we're using the 555. I will say that you don't have to use the 555. We have a full line of analyzers, and depending on what the device under test is, one or another analyzer may be a better choice. And then I have three specific sample devices that we'll take a look at today. The first is just a very simple ADC. So this is a device with a unbalanced or single-ended analog input using RCA jacks. It's a consumer device, and it has a SPDIF output. The second device is the counterpart to that. So this is a digital to analog converter. It has a SPDIF input and single-ended analog outputs. And then I also have maybe a more typical device if you're evaluating DAC and ADC chips. In this case, I have a bare evaluation module for an analog to digital converter. And so this device has a balanced input and an I2S output, and we'll be interfacing to this device using the digital serial interface on the APX. Okay, so throughout this presentation, I'll be diving back and forth between APX software and this PowerPoint presentation. Let me take a moment to talk about the APX 555 itself and why we're looking at that today. So when we're testing digital to analog and analog to digital converters, there are several figures of merit or measurements that we want to make that we can only make if essentially the analyzer's performance exceeds that of the device under test. So, for example, what I'm showing on the screen right now is actually the analyzer looped back on itself. I do have the devices under test connected in parallel, which is a little tiny bit of an issue. But what you can see right now is I'm generating a pure sine wave out of the analog generator and measuring it with the analog analyzer. And what you can see here, where we're looking at THD plus N, is essentially the analyzer's residual self noise and distortion. And this defines a bit of the lower bound for a device that we could measure. That is to say, if we were measuring a device that had itself a THD plus N less than minus 120 dB, it would be difficult to measure it because it would be we would be unable to separate the residual noise and distortion of the analyzer from the residual noise and distortion of the device under test. If I turn the generator on, turn the generator off, this one's a little bit trickier. I'm just going to unplug a couple cables for a moment. And we'll take, so now we're looking at the analyzer's residual self noise. So again, if we wanted to measure the noise of a converter, we would reach the threshold of the analyzer at something a little under a microvolt. Now, another figure that may come up is if we want to test a device's frequency response all the way across its passband. So let's take a look at that for a moment. So what I'll just do now is I'll sweep the, again, the analyzer itself, and I'll sweep it, say, from 200 kilohertz to 20 hertz. Now, testing a DAC or an ADC, in this particular case, we'd probably be looking at an ADC. The reason that this would be interesting is it would let us sweep a converter not just across its full bandwidth, but through the transition and stop band of any anti-aliasing filters in that converter. And so what we arrive at is really three properties that the APX 555 has that make it uniquely suitable for testing DACs and ADCs. The first two are closely related. It simply has the lowest self noise and distortion of any audio analyzer in the marketplace. And then the second is that it has the broadest usable passband or bandwidth. So it will measure up to 1 megahertz bandwidth, and we can generate a signal up to 200 kilohertz. And so that lets us sweep across and beyond the full band of the vast majority of converters. So the next thing I want to talk about, and we'll just go through configuring each of our sample devices, is some of the choices we have in input and output configuration. So on our analog output, we have three choices. We have analog unbalanced, analog balanced, and if you have a 555B or a 555 with the enhanced analog generator option, there's an available analog balanced ADC test. I'll talk about these each in turn. Analog unbalanced, the key difference between balanced and unbalanced configurations, and maybe we're used to seeing RCA connectors or XLR connectors, the key difference is actually that a balanced connection, both the low side and the high side have equal impedance to ground. And in this particular webinar, we won't get into all the reasons why, but the long and the short of it is that what makes a connection balanced or unbalanced is that both sides of the circuit have equal impedance to ground. Now, we commonly associate balanced circuits as also being differential. That is to say that the signal has a positive component on one side and a negative component on the other side. But that is actually not the part that makes it balanced or unbalanced. And it's actually possible to have a balanced interface that's not differential. And I suppose, particularly in the case where something went wrong, you could have a unbalanced interface that was differential. For both unbalanced and balanced, some of the choices are available are the source impedance of the signal generator. Generally speaking, this is left at the defaults unless there's a specific use case. So for example, matching the impedance of a circuit, or in particular, there are still some classic 600 ohm circuits in the field. The second is you can fix the output range in order to sort of always provide an optimum residual noise and distortion from the generator. The generator does in fact have multiple output ranges. By default, this is managed automatically by the system, but you may encounter devices that have extremely sensitive inputs, and the transition from one output range to another does produce a small transient, and that might upset the device. So this is a location where that might be fixed. The balanced output looks very similar. Again, here we do have the ability to set the source impedance. We can again also fix the output range, but there is a little bit of a new one, which is that one thing that is done on balanced circuits is it's desirable to measure the ability of the circuit to reject a common mode signal. Generally speaking, the great benefit of balanced circuits is their ability to reject common mode noise. So as a figure of merit, it's often desirable to measure the common mode rejection. And we have a specific measurement for doing that, but also in the configuration of the output, you can change it from normal, which would definitely be the most common default, to an array of choices that essentially take the balanced circuit and impair it. There's so-called common mode test, IEC pin 2, and then pin 3. The difference between common mode test and IEC common mode test is in common mode test, the same signal is applied to both the positive and minus pin of the circuit. That is 100% common mode signal, so to speak. In the IEC version of the common mode test, the two legs are actually unbalanced purposefully by a small amount, a few ohms, to more realistically simulate, I'll say, an off-the-shelf transmitter, which typically don't have perfectly balanced circuits. And then single-ended, which will actually just take the balanced output, the physical connector of the APX, and convert it into a single-ended device. Our third analog balanced output choice on the 555 is what's called ADC test. This is perhaps a little bit misleading, but what this provides is all the same controls as a standard analog balanced output, but we now add the ability to set what we refer to as a V bias, but is actually a common mode DC bias. So the same DC voltage is applied to both sides of the balanced output.
Hey, Dan, I've got a question for you.
Yes.
The question is, what is the analog output transit time when it changes range, assuming that I set it to auto?
So if you set it to auto, the transit period from, or really the range change time, is in the period of milliseconds. Now, when you have auto range enabled, all of that is, so to speak, hidden. That is to say, the analyzer itself knows when it changes the output range and coordinates that with the input side. So no measurements are made during the range transition period. And the timing of that actually does vary, but it's generally measured in milliseconds. Okay, if that did not satisfy the questioner, please feel free to follow up with another chat and we can address that as well. So finishing up here, just where is the application for common mode DC? The reason we call it ADC test is actually this arises primarily in the case where we're testing ADCs that are designed to be interfaced directly to something like an electret microphone, where there's going to be a DC bias present, and we want to essentially simulate that. Okay, so let me just plug some cables back in. And let's take a look at the input side of this equation. Let me disable loopback. And let's take a look, actually, first let's take a look at our ADC. So actually I want analog unbalanced output. And really for this particular device, I'm not going to change any of the default settings. My input is going to be digital unbalanced. Now, here's a place where we should disambiguate some audio precision terminology versus the rest of the world. On an audio precision analyzer, digital unbalanced is essentially synonymous with SPDIF. Now, this is SPDIF / AES3 / IEC 61937, but it's a single-ended digital interface. You'll see this on some professional equipment, some consumer equipment. And we can kind of see immediately that the system is alive. In our FFT spectrum monitor, we see the output spectra of the device. We see the noise of the device in dBFS. And down in our status bar, we can see input 1, digital unbalanced, PCM, 48 kilohertz sample rate. Now, at this point, I'm actually pretty much ready to test. I'll talk later in the presentation about measuring jitter, but the only additional settings that I might look at is if I want to apply some filters to these signals before I even make a measurement. So for example, if I might want to look at the DC component of the signal. The default is to AC couple it. I can also apply sort of an arbitrary high pass filter if I want. So for example, I might say I want an elliptic or essentially a brick wall filter with a corner frequency of, oh, I meant 20 hertz, not 20 kilohertz. And if I want a low pass filter, now essentially with any digital input, there's going to be a low pass filter of Nyquist. So FS, or the sample rate divided by 2. I could again also select, I want a 20 kilohertz low pass filter. It's not essential to make a filter selection in signal pass setup. Each individual measurement also has the ability to make a filter selection. The reason to make a filter selection in signal pass setup is if you want to sort of globally apply a particular selection. I'll say that the most common of these is to choose whether you want to be AC or DC coupled. And I'll down the road make some measurements, and those measurements I'll make specific choices, but I'll just go ahead and say that I want the interface itself to be DC coupled. Now, to verify that this is all actually up and running, I can go ahead and verify my connection by turning on the signal generator. I'm generating a 100 millivolt signal, and I'm getting a response back from the device of about -23 dBFS. And again, in the lower left-hand corner in our input signal monitor, we can see that spectrum of that signal as well. Now, I'll turn around and take a look at our DAC. Our DAC is almost perfectly the reciprocal. So it has a speed of input, or a digital unbalanced input. So I'll select digital unbalanced as my output. And it has an analog unbalanced output. So I'll select that as the input on the analyzer. Here you can see a couple things. First of all, we do immediately have signal from the device. You can see this device has a very significant DC offset. So in this device, maybe I will go ahead and select AC coupling just to remove that DC offset. Now, since we're looking at an analog input, we do want to select our measurement bandwidth. I'll go ahead and just select 22.4K as our input bandwidth. So that means the internal analog to digital converters will be run at 48K in the analyzer. I'll otherwise leave other selections alone. And I'll turn on my signal generator. And at -20 dBFS, so that's the signal I'm digitally generating, I get a response from the device of 78 millivolts. So that device is up and running. And for today's exercise, frankly, I'm using these sort of consumer off-the-shelf devices because they're relatively straightforward in terms of configuring their inputs and outputs. But now let's take a second and talk about the EVM, or evaluation module, that I also want to test this morning. It has a less simple interface. It uses our digital serial I/O module to communicate with the device under test. And this device definitely has a lot more settings. So first, a little aside about the DSIO hardware itself. On the front panel of the digital serial I/O module, there are 4 high-density D-sub connectors. There's a connector for the transmitter. You might think of that as the generator. There's a connector for the receiver. Those are both on the top of the panel. For the transmitter and the receiver, we also provide an electrically buffered monitor connector. One of the things that's extremely useful when troubleshooting serial data interfaces is to be able to look at the actual signals on an oscilloscope. And in many years ago, this would be done simply by directly probing those circuits. But as the data rate has gone up, the fact that the probes add resistance and capacitance may themselves impair the connection. So on the digital serial I/O module, we actually provide electrically buffered connections that are snooping on the interface signals, but are not electrically loading it and can be connected directly to an oscilloscope. So on this slide, you can see the 3 standard cables that are available. So the first is a standard, well, I shouldn't say standard, an audio precision cable that goes from the high density connector to square pin headers. This is the most common kind of connector you will find on eval modules. The second goes from the high density connector to BNC terminated connectors. That's very convenient for the monitor, since of course those BNCs will plug directly into every oscilloscope I know of. And then lastly is a new option we've added in the last couple of years, which is a low capacitance short cable. So one thing that we'll talk a little bit about is at sort of moderate sample rates like 48K, you can have a pretty long serial interface cable. But as that data rate goes up, the interface cable itself, its capacitance and its resistance will start to interfere with the signal. So to support high sample rates, low drive voltages, and the like, we now also provide a short, low capacitance cable. Now we do use a non-standard connector for the DSIO interface. It's this HD15. We don't do that for any nefarious reason other than there's just a lot of pins and we need to get them on the connector. So we do in fact publish the pinout. HD15 connectors are of course pretty readily available. So we do have more than a few customers who will fabricate their own cables, or you will actually find some evaluation modules in the world are manufactured with this HD15 connector on them, so they can be interfaced directly to a DSIO quite conveniently. Okay, this chart I think gets at the crux of why configuring serial interfaces can be difficult. To be perfectly honest, there are no standards. The closest thing that one might call a standard is I²S. But even that is really something that was published by Sony in a technical article maybe 30 or 35 years ago with the advent of the first CD players. And what's really going on is that each manufacturer of a chip level device publishes a timing diagram for the data interface. And we've sort of come to understand some very common formats, I²S being by far the most common, but you'll also see references to right justified or left justified or DSP mode. Frankly, these interfaces are all at a physical layer very similar to each other. They're typically a 3-wire interface. There's a bit clock. Now, not everybody uses the bit clock terminology, but in one way, shape, or form, there'll be a bit clock. The one which is the next most ambiguous is here at AP, we call it a frame clock. The next most common term you'll see is a left-right clock, or LR clock, in the displayed timing diagram. And then there is the blocks of data themselves. Now this is for the most common type of interface. You'll also see interfaces which people might describe as TDM, which are very, very similar, except instead of having just 2 channels of data on a data line, they might have 4 or 8 channels or even more, all multiplexed onto one data line. The other thing that is commonly done is to just have multiple data lines. And then what many, if not all of the settings come down to is what's the relationship between these different signals. And I'll get into that a little bit in just a moment. Okay, so this is not a picture of exactly what I have connected today, but it generally communicates the idea. I think many of us have seen or work with these things, particularly when we're in the early stages of designing a new product. We're considering different devices, so we acquire or purchase different evaluation modules. And so this is what that might commonly look like. The evaluation module that I'm using today requires plus minus 15, plus 5, and plus 3.3 volts for power. So I've got a DC power supply set up for that. I've got analog audio going into it through a balanced connection. And then I have the DSIO's square pin cables going to the device under test and the APX. So let's talk about some very common problems with the physical connections. These serial data interfaces are circuit board level interfaces. On a finished device, I²S is typically not going to run more than inches between two devices. So having an 18-inch or longer or shorter cable is still typically much more than the devices were meant to drive. Those cables introduce resistance and capacitance. And one thing you can kind of see on the screenshot from an attached oscilloscope is that instead of having nice sharp square waves, we have some rounding of the leading edge. We sometimes call that shark toothing. So in general, keep your cable short as possible. Think about your grounding situation. In my particular case, I realize you can't see it physically, but I've carefully set up a star ground where the APX analyzer itself is the star, and I have ground straps for both the digital ground of the EVM and the analog ground of the EVM going back to it. And finally, don't leave dangling cables, right? Don't connect a cable to the DUT, and because you're not using that interface, just leave the cable flapping in the wind. These are all things that will impair your physical setup and may result in things just not working. When I'm setting up a serial data interface, I find the monitor ports of the DSIO extremely useful, because essentially what I'll do is I'll connect the monitors to an oscilloscope, and I'll look at what's actually transiting over the wire. I'll compare that to the timing diagram that the APX renders and the timing diagram in the data sheet that the device I'm testing provides. And if all three of those coincide, life is good and everything will work. And if one of those does not coincide, I'll troubleshoot that problem. And you know exactly, I may have the device under test misconfigured. I may have the APX misconfigured. I might have a physical problem as well. But this is, in this particular screenshot, this is exactly what you can see if you connect the monitor ports to your oscilloscope. Okay, so today we have a pretty simple setup. We're looking at a 2-channel analog to digital converter, so we're going into it balanced analog, and what's coming out is I²S data. And I'll show you what this configuration actually looks like. But essentially here you have this relationship. I have the view from an oscilloscope of what's actually going out over the wire. I have the settings in APX software and then the rendering of the timing diagram that it makes. So let's just take a quick look at that case. So I'll set up my output as analog balanced. I'll set my input as digital serial. And whereas with analog and SpeedIF, probably the only selections I need to really make are to choose that that's the interface I want. With serial interfaces, I'm going to click on my little gear icon. And that's going to bring up my DSIO receiver settings panel. And in this case, no accident, I did set this up so it would be relatively easy. I have a single data line. I have 2 channels of data. It is the most significant bit first. Now we have a couple formats baked in and you can choose your own, but this is a I2S interface, and I2S means the data is left justified and the frame clock is 1 subframe. The word is 32 bits wide, even if it's only 24 bits of data. Now, a couple changes I do need to make on the clock side is we are generating our own master clock, and we're providing that clock to the device under test. So the device under test is not free running it. We're sending it actually a master clock, a bit clock, and a frame clock, and we are setting those. So there we go. Once I turn all the transmitters on, the device comes alive. You can see the noise floor in DBFS. And if I turn signal generator on, I get a signal back. So I'm generating 100 millivolts and I get minus 38 dBFS back. So that's all 3 of the devices we're going to take a look at this morning or this afternoon, as the case may be, all up and running. Okay, so before we get any further, let's take a small moment and talk about physical units. If we were testing an analog audio device, we would be talking about actual physical units. We'd be talking about volts, or perhaps we would be talking about pascals of sound pressure. There would be some physical unit. With digital audio, with converters, we're just talking about 1s and 0s. So what's the amplitude or level of that unit? We're probably all pretty familiar with the notion of FS, or full scale. Audio precision has an additional unit we use which we refer to just as D. Maybe it means digital. The difference, the reason we have these 2 units is in the physical world, in the land of volts, volts is both an instantaneous unit and a RMS unit. In the digital world, for I'll say historical reasons, FS, or full scale, is only an RMS, or root mean square unit.
Hey, Dan, I have another question from an attendee for you. Just wondering if there is any specific reason there is no 192K BW for 384K SR on the analog unbalanced input. He says it goes from 90K BW at 192K SR to 250K BW at 624 SR. Any comments there, Dan?
Yeah, that's a great question. So what's actually going on behind the scenes inside of an APX analyzer is up to 192 kilohertz sample rate, or roughly 90 kilohertz bandwidth, we're using one set of analog to digital converters. And then to go to the next step in bandwidth, we actually go to a completely different converter that operates at a much higher sample rate. So that's why there's that sort of step function, is that there's internally to the APX 555 a gear change. Okay, so to go on about units. So there actually is no standard, and here I really mean the capital S standard in the world for instantaneous digital amplitude. And in the absence of that, here at AP, we're just using this unit D. So in the APX software, when you're measuring the RMS amplitude of a digital signal, that will be in FS. And when you're measuring the instantaneous amplitude, that will be D. So the definition of FS and dBFS, so this actually comes from the Audio Engineering Society has a standard, AES 17. And what the standard says is full scale is the RMS level of a sine wave where the positive peak reaches the maximum digital code. So the issue with this, if there is an issue, is that not only does that mean that 1 FS or 0 dBFS is scaled to the full scale amplitude of a sine wave. That means that with the right signal, a square wave, for example, you can in fact have values that exceed 1 FS or 0 dBFS. So this is just a quick aside that I'll show you, but you can show or refer analog levels, particularly in DAC and ADCs. We often want to think about, for a DAC, the output relative to its maximum voltage output. So that's really the gain or sensitivity function of the device. Okay, so as I said before, where we can get into trouble is, number one, with FS, the signals can be greater than 1 FS or 0 dBFS. The worst case would be a square wave, where the peak amplitude of the square wave reaches 1D. That would be a RMS level of 1.414 FS, or plus 3.01 dBFS. And the second is plotting things instantaneously. So for example, in a time domain view. In a time domain view, we're looking at instantaneous levels, and in that case, we can only use an instantaneous amplitude unit, which for AP is D. Okay, so I realize that's all a bit of an aside, so let's jump into some measurements. All right, so the first thing I'm going to jump into is, let's take a look at our ADC. So I'm going to configure my output as analog unbalanced and my input as digital unbalanced. By the way, I'll just call your attention to one thing, which is that in SPDIF or AES3, the transmitter controls the sample rate. So in this case, the transmitter is the device under test. When I test the EVM, we're controlling the sample rate because we're over I²S providing the clocks. But in this particular case, the device is sending us audio at 48K. We don't have any control over that. That's just the way it is. So the first thing I'll take you to is a display here called bits. This can be quite a useful tool for troubleshooting the setup of our digital interfaces. So this has two displays, active bits and data bits. So data bits is showing the instantaneous value of each bit in the digital word. Active bits fills in every bit that has transitioned states in the last second or so. And what this is useful for is this tells us right off the bat that this is a 16-bit audio device because the upper bits are not changing states, so they're just not being used. Now let's take a look. I'll briefly go into just a little bit of an arbitrary case, but let's just look at our digital optical and loop that back for a second. When troubleshooting a digital connection, there are a couple more useful things I can do with the bits display. So I'm going to change this to data bits. And in my verify connections, I'm going to change this from sine. Let's do walking ones. And I'm going to set the samples per step to 4,800. Now let's slow that down. So now I've set the samples per step to equal the sample rate. So what this is doing is literally raising the value of each bit and changing it every second. So we can literally see the data walk through the word. There's the inverse of that, which is walking zeros. And then a little bit of an alternate, which is constant value. Constant value is particularly useful if you're trying to diagnose data interface problems on a serial connection, because, for example, if I change this to AA, oops. There we go. So this is just a very simple data pattern. If I was looking at this on an oscilloscope, I'd directly see the high and low bits of the actual data word on the oscilloscope. And if data was getting mangled, I'd see that right away. So this just generates a constant pattern for the digital word. It's really not audio data at all. Okay. So back to our ADC. Let's look at a few things that we can learn about this device or any device right in signal path setup. So if I turn on my signal generator, and here we're just generating 100 millivolts, we're getting back minus 23 dBFS from the device. If we look at gain, now if this was a device that had analog input and output, and we looked at the gain function, we would see this just in dB, but here we're crossing domains. We're putting an analog signal into the device, and we're getting a digital signal out of the device. So maybe dBFS. So this is showing us that I'm getting minus 3.2 dB per full scale per volt, or dB full scale per volt. So that's the actual gain, or if you will, sensitivity function of this device. Now, another thing I might want to know is, well, what's the maximum input level of this device? So I'm going to go to my references panel. Maybe I'll undock it. And I'll use our automatic generator level function.
Dan, I've got another question from an attendee.
Sure.
Is this serial interface included with APX 500 Flex by chance?
It is not. The APX 500 Flex is essentially APX 500 software by itself combined with a third-party audio interface. So the digital serial interface is a hardware option for one of the APX 500 modular hardware analyzers. So it is not available with APX 500 Flex. Okay, that is an excellent question. Let's take a look at automatic generator level. So here we can have the system automatically find an input level for the device that satisfies a couple of different output conditions. The first is I'm going to try saying, hey, I want to find out what input level gives us an output level of 0 dBFS. Essentially, at what point do we reach full scale for this converter? And I'll tell it to look between 1 and 2 volts. Okay, so what it's found is actually an output level from the analyzer or an input to the device of 1.442 volts RMS, gives us just about exactly 0 dBFS. Now, let's take a look at THD plus N. It's still all right if we look at it as percent. Let's take a look at the reciprocal device. So let's look at our DAC. So we'll go digital unbalanced out, analog unbalanced in. Now here it's maybe simpler. I could just drive this device at full scale. And it is not too shabby. So that's probably what I'd use as a reference there. The other thing I could use as a reference is I could regulate to a target distortion. So this would be the case if you had an analog to digital or digital to analog converter that clipped or perhaps compressed before reaching full scale. Now, for both of these converters, that is not an issue. Oops. Okay. So now let's just look at some simple figures of merit. If we go to our level and gain measurement, set our generator to full scale, that tells us the output. So at this this device at full scale, we get 780 millivolts per full scale. And the gain is essentially the same function since we're already driving it at full scale. Now the difference between gain and level is if I go minus 20 dB, the gain function is the same, but having gone 20 dB lower, we're getting 20 dB less output signal. Next, I'll take a look at THD plus N. This measurement is not quite as simple. So again, we can start at full scale. Oops. And so we drive this DAC at full scale. We get a THD plus N of 0.003% or minus 90 dB. We can also look at the absolute level of that. So the residual noise and distortion when stimulated at full scale is 20 to 24 microvolts. And we can keep parsing that. We can look at just a distortion ratio or just a distortion level or just the noise components ratio or level, or the ratio or level of individual harmonic products. We can look at the frequency response of the device. So there are a few different takes on this, whether frequency response should be run at full scale or below full scale. And the issue there is if the device has some positive frequency response excursions, you may drive it into clipping. So I'll say that typically frequency response is measured well below full scale. And here, if we go to relative level, we can see that there is a small rise in frequency response, maybe 3/4 of a dB as we get at high frequencies. I'll show you the transition and stop band response in a moment. Now let's talk about noise and signal to noise ratio and dynamic range and SINAD and a few other measurements, which are all kind of dancing around the same question, which is what's the self noise of the device and what's the ratio of that to, I'll say, the maximum signal that a device can express. So signal to noise ratio, this measurement in APX is pretty straightforward. The device is going to be stimulated at the level you set, which in this case is full scale. We'll measure that. We'll turn off the signal generator. We'll then measure the residual self noise of the device. Now in this case, I've applied a 20 Hertz and a 20 kilohertz high and low pass filter. And then that's expressed as a ratio, 95 dB, pretty decent. Now let's add dynamic range.
Dan, I've got another question from an attendee.
Okay.
Are there any limitations of doing the same sequence in PDM, as in PDM generator and input, or PDM generator and analog input?
Basically, no. So, you know, there's a lot of different kinds of analog to digital and digital to analog converters out in the world. And one kind that I'm not specifically talking about today, but is definitely out there, is things like MEMS microphones and Class D modulators for power amplifiers. These are definitely a little bit of an odd duck in terms of converters, because they are 1-bit converters, and that's a whole thing we can get into separately, but fundamentally they are still devices that either take a digital signal and render an analog signal, or sample an analog signal and render a digital signal. So in and of itself, all the same measurements are valid, but there may be some peculiarities to the device itself. So one that I'll say comes up the most frequently is when we're looking at delta sigma modulators. There is, to our knowledge, no delta sigma modulator that can be fed a full scale signal without becoming unstable. So in particular, the delta sigma modulator we implement inside of APX for the PDM module, it only accepts, my memory is not quite perfect on this, but I believe it's some dB less than full scale is the maximum signal it will generate. So that's an issue. But I think to the core question, it's still a digital to analog or analog to digital converter, and these measurements remain relevant. Okay, so that was signal to noise ratio. Now let's talk about dynamic range AES 17. So this is a little bit of a different case. So in the AES 17 standard for maximum confusion, this measurement is in fact referred to as signal to noise ratio. We named it something else because it has some different connotations in the wider world. But in this measurement, again, we drive the device with a full scale signal, but then instead of turning the signal generator off entirely, we turn the signal generator down by 60 dBFS, and we then remove that minus 60 dBFS signal from the output with a notch filter. And the goal here is that many devices, in the absence of any signal altogether, will mute themselves. So what you can see here is, well, we had 95 odd dB in signal to noise ratio, but in dynamic range, it's a little bit different. Now there is also a different weighting filter used, different high pass and low pass filters. So let's equalize those out. So almost identical result. Then there are measurements of just the idle noise of the device. So here we're looking at just the noise of the device in absolute volts. And then sometimes you'll see a desire to measure what's called the quasi-peak noise. This is a little bit of a more obscure standard, but does hang out in some measurements looking at converters. So just respecting our time, I will jump to, well, I think I'll just jump quickly to jitter for a moment. So I'll go back to signal path setup. So let's turn our signal generator on. Okay, so if I go to the clocks configuration, one of the things that an APX 555 can do is apply jitter to the device. And this is essentially what we'd call an impairment. We'd want to see how well does this device perform under less than ideal circumstances. So we can take this device as an example. I'll turn on our jitter generator. We're going to generate a sine jitter. So this is a little bit confusing, but what we'll do is vary the period of the clock relative to an ideal using a sine function at 1 kilohertz. And let's actually do that at 500 hertz. And let me pull up this FFT monitor.
Dan, I do have another question from an attendee.
Mm-hmm.
Are there any solutions to SACD playback performance?
That is a, I can either answer that very easily, which is to say yes, but it's sort of a bit of a more complicated question. On face value, the big issue with SACD playback is that there's a much higher bandwidth compared to a CD. So you might need to be measuring out to 40 kilohertz or even 90 kilohertz. But that part is physically straightforward to do with an APX. All of our APXs have sufficient input bandwidth to make that measurement. So I would say that, the answer is yes, but we might need some follow-up to get at exactly what we want to measure. So in this case, the reason I selected 500 hertz as the jitter generator's frequency is exactly what we get in this device is these side bands to the fundamental at 500 hertz. So you can see we have one at 500 hertz and one at 1.5 kilohertz. And that's the impact or response of this device to jitter. Now this is pretty severe jitter, 1 UI, but you'll definitely see that different converters have better or worse jitter rejection mechanisms. The converse of that, if we go back, analog unbalanced and digital unbalanced input, is I'm going to switch this measure from audio to jitter. So in this case, we're receiving a jitter signal That is to say, we're no longer measuring the audio signal that's embedded in the digital interface. We're measuring the digital interface itself, and now we're looking at the amplitude of the jitter that's coming in from this device. And this is where I was referring to an entire UI being quite a bit of jitter. The residual jitter of this analog to digital converter is, less than 1 micro UI or unit interval, which is sort of a sample rate independent view of jitter.
Daniel, I have another question from an attendee. What
Sure.
if I want to measure the ADC performance of a device with USB audio class interface, which might serve a microphone bias voltage on a single-ended mono input? Do I have to use the analog balanced or ADC test output and the ASIO input? Also, can it be sufficient to just use the analog unbalanced output here?
Let me take a moment to unpack that. So we have a device. It's a USB audio device, so I assume it's like a USB headset interface. It has an electret mic input. So if the I probably need to, or we would probably need to look at actually a little wiring diagram to make sure we're not answering this incorrectly. But offhand, I would say that that's exactly what ADC test mode is for, in terms of it can provide that DC bias. If that's not required, so for example, if that can be disabled, if it's not essential to the test, then probably a single-ended interface can be used. As far as the physical interface, it sort of goes a little bit beyond the scope of this webinar, but we actually have an upcoming webinar on this topic. You'd have two choices. You could use the ASIO interface potentially to bridge across to USB, or you could use what we would refer to as open loop test, where essentially we would record or play back WAV files and then analyze those WAV files. Those are both potential solutions to that problem. So if you'll bear with me, I realize we're running a little late, but I just want to show you a couple remaining measurements. So let's just quickly take a look at a step level sweep on this particular device. So here we're simulating the device at a constant frequency, but varying the signal generator level. And what we're looking for is the linearity of the device. I might have, give me 1 second. Oh, yeah, that would not help. And the main thing we're looking for when we test any converter is this particular graph isn't so exciting. But here what we have is an amplitude linearity graph. And what we're looking for here is the range over which the gain function of this converter is flat or linear. And what you can see is just above 1 volt is where we get to the clipping point of the converter, and that's where it becomes nonlinear. The other thing we can look at is here is the distortion of the converter as a function of its output level. So this is a pretty classic chart. At very low levels, it's of course noise dominated, and then there's an operating region where it's basically dominated by distortion, and then we hit the clipping point of the device. And then what we can do is just take a look at the, let's call it the transition and stop band response of this device. So we're going to do a frequency sweep from 20 kilohertz to 30 kilohertz. And we can see a couple things here. So here you really see the performance of the anti-aliasing filter, and that's typically most challenging right at Nyquist, and you can see some interesting behaviors. First, if we look at THD plus N ratio, it actually climbs, and that's probably because we're getting some aliasing products when we get very, very close to Nyquist and just beyond. And then, of course, we can also just look at the how good the rejection of the filter is. So I realize that that's become a little bit abbreviated, but I'd just like to respect everyone's time. Just take a few moments to address any questions people may have.
Dan, I just had a question come through. Can you comment on when using a stepped or using a continuous sweep?
Sure. That is a good question. There are some subtle issues there. So the continuous sweep is Audio Precision's implementation of Angelo Farina's exponential sine sweep technique, and it has a lot of things going for it. So the first is that it's very fast. It is unquestionably the fastest sine measurement technique currently available. The downsides, particularly in the context of testing DACs and ADCs, is number one, it's digitally synthesized. So that is to say, it itself is generated by a DAC. And I don't want to get into any of the can you measure a DAC with a DAC kind of questions. The key thing is that in an APX analyzer, to get to very high signal generation frequencies, we need to use our analog sine generator. So to generate a sine wave at 200 kilohertz, we can't do that with a DAC. So if you want to sweep above or even close to Nyquist of most converters, any converter certainly that will go to 90K or more, you need to use the analog generator, and that precludes using a continuous sweep. The other downside is that continuous sweep, the Farina sweep, only measures THD. It only measures distortion. It does not measure distortion and noise. And that's key because in a converter, we'll be looking at things like alias products, standing tones, spurious tones, dither artifacts. All of these things are noise in the sense that they're uncorrelated signals. They're not harmonic distortion. So those types of products will not be measured with a continuous sweep. If you want to measure frequency response inside of the passband quickly, continuous sweep is an excellent choice. If you want to measure through the transition band and into the stop band, and you want to measure noise, then step frequency sweep remains the best choice.
All right, I've got more questions lined up for you, Daniel. First question, I will be using an APX 515B. Can the two digital signals be made to produce different values for a DC level sweep?
That is actually a question I don't know the answer offhand. I'm going to say I believe so, but let's just check. So the answer directly is no. The DC offset's going to be the same. Well, actually, let me. Sorry, I'm wrong. You can, if you go into advanced settings, generate both a different amplitude value and DC offset value on both channels. So just go into advanced settings, uncheck levels track channel 1, and then you can set a different amplitude and DC offset value per channel. And if you select sine dual, you can, generate a different frequency, amplitude, and DC offset on both channels.
Great. Okay. Thanks, Dan. Next question is about signals that are damaged caused by long cables with the DSIO module. Does Audio Precision have external buffers like the PDM line driver that exists for the PDM module?
We do not. It is possible that that could be used. It depends very, very much on the clock configuration. So what I'll say is in most serial interfaces, not in all serial interfaces, they're what we would call source synchronous. That is to say, all the clocks are going in the same direction. So for example, in the device I'm testing today, the APX is the source of the master clock, the bit clock, and the frame clock. However, in some devices, you provide one clock and then the device uses that clock to synthesize and return a different clock. In those situations, a buffer is not particularly going to help you because what you're going to run into is what we refer to as clock in to clock out delay, which is the absolute amount of time you have from when the device receives a signal to when it needs to turn that signal around. In general, the energy is best expended reducing your cable lengths. I realize that sometimes that's just not possible, but in general, you'll be more successful with that. The next most successful technique is actually to look at the termination on both ends. Usually you have a discontinuity in termination on the serial interface cables. So it may be worth calculating out and actually adding a resistor so that you have matched impedances on the cable. That would probably be the next most successful place. To be honest, I've never tried using a buffer. I think it could probably work in some situations, but unless there was absolutely no other choice, I would try a few other things first.
All right. Next question. Is there a specific reason in the graphs that you use the stepped sine instead of a much faster chirp?
Yeah, I think that's the question I answered previously, which is depending on what frequencies you want to be able to sweep to and what measurement results you want to get, you sometimes just can't use a chirp. So in this case, I wanted to sweep the device into its stop band, and critically, I wanted to measure THD plus noise, not just THD.
Thanks. Another question, what does one use as signal source for SACD playback measurement?
That's an excellent question, which is code for that's a difficult question. The answer is if we're talking about you have an actual SACD player, then you would need a test disk, which you might have to make yourself, though I believe the Japan Audio Society did create some SACD disks with recorded test signals or synthesized test signals. That would frankly be the easiest. If we're talking about testing a chip that has an SACD physical layer interface, and this gets a little complicated, but SACD is pulse density modulation. That is the physical signal itself. That can be synthesized actually by a PDM module. The downside to the PDM module is that SACD uses one data line per channel, and the the PDM module has only one data line, so you would only be able to test the left or right channel at a time. But that would be another possibility, and there are many steps in between, because there are some things that support SACD over I²S and some other things. So that might be an answer where we need to get some more detail about the physical device under test to usefully answer that question.
Okay, thank you, Daniel. I have another question asking for a demonstration of SYNAD measurement, SIAD. Yep.
Sure, I kind of ran out of time, but let me take a look at that. So for those who may not know, SYNAD or SYNAD, I'm not actually sure what the correct pronunciation is the reciprocal of THC plus N. It really is 1 over THC plus N, and it's expressed in dB. And actually for this device, let's look at SYNAD on the DAC. And let's do this at 1 kilohertz. I'll say, oh, and let me disable the jitter generator, or this device is going to look much worse than it actually is. So, and especially if we look at SYNAD in dB, you'll notice that this is just positive 90 dB instead of minus 90 TH. So positive 90 dB SYNAD instead of minus 90 THD plus N. Now there are some other smaller considerations with SYNAD, but that's SYNAD. It's just, I probably shouldn't say just, but it's the reciprocal of THD plus N. The other thing I actually think is more interesting is the other result that we have in SYNAD is the equivalent number of bits. So in a PCM sampling system, every bit is equal to 6.02 dB of dynamic range. Now, A to D converters and D to A converters are not perfect. So the question then becomes, well, how close to perfect are they? And so, again, there's a little bit more detail into it, but the basic thing is we can take the SYNAD or the THD plus N and divide it by 6.02 dB, and that tells us how many useful bits we're actually getting. So in this case, you can see that in this converter, we're actually pretty close to its theoretical 16-bit performance. We're getting 14.7, 14.8 effective bits.
All right. Can you also measure phase and group delay? It's another question I have.
Yep, so let's take a look at that. And so this is one where I will use our continuous sweep measurement. And let's so we're sweeping the device with a Farina sweep. We get its frequency response again, but now let's look at a couple things. So here's phase, and this is the inter-channel phase. So this is the phase from the right channel relative to left channel or channel 1. Now the other thing we can look at here is the input to output phase. So if you will, this is the phase relative to the generator. And what we can see here is that this is linear phase or just delay. And if we looked at the impulse response, it's obviously very small, but we can see the actual delay there. And then getting to what was actually directly requested, we can see the group delay. Now, the interesting thing here we're seeing in the group delay is this dealy bob at the beginning. That's really AC coupling filters settling. So this is one area where I'm going to go back to signal path setup, and I'm going to change my input coupling from AC to DC. And I'm going to do the sweep again. And now we're not conflating any AC coupling in the analyzer with AC coupling in the DUT. Now we're just seeing the group delay of the DUT. And for those who are curious, we do have a couple of small features. What's going on here is we can see that this DUT, if we look at just its idle noise spectra, has a couple of idle tones. I can only speculate what the source of those are, but it has a couple idle tones at those frequencies, and as the sweep passes by those frequencies, they get conflated. But here we have the group delay of this converter.
All right. One final question for you, Daniel. Adds a little bit of background. When measuring impulse response with the continuous sweep, sometimes the impulse response is not showing correctly. As an example, it is supposed to be a linear phase filter, but the impulse response is not symmetric. Is that because of how the impulse response is derived from the continuous sweep measurement?
I would say the direct answer to that is no. We'd probably want to dig into that a little bit more to see what's going on. For the the impulse response in continuous sweep is derived by the deconvolution of the response waveform to the stimulus waveform. So that in itself is not going to cause the impulse response to render incorrectly. I'd say that just generally things we've seen that may cause errors in the impulse response is devices that don't have constant delay. Worst case imaginable might be a Bluetooth device where the actual delay of the device varies in time. Not having too much or too little delay. So in that particular case, I would suggest that we don't have an easy answer, and we should reach out to that person and talk about their specific device under test.
Okay, thank you, Daniel. Thank you everyone for attending. Great questions from the group. So thank you for your participation. We're really excited to be presenting this to you. I wanted to share a few resources that are available to you that are on the internet. So bear with me as I get my screen pulled up here. So there are some resources available to you, one being our Audio Precision website, www.ap.com. We have a variety of assets from application notes to tech notes, articles, data sheets, white papers, and more. So if you want to learn more, feel free to visit our website. We also have a blog that is regularly updated with new posts about all things audio test and measurement, from THD plus N to multiple simultaneous input types. We have a variety of resources available to you there as well. Also, feel free to follow us on social media. We are present on LinkedIn, Twitter, Facebook, and Instagram. And of course, we also have YouTube. We have videos that are our APX test sessions, where we do a deeper dive into specific applications and test setups. And we also have our quick tips, which are short tips that are available for you to utilize as guides for your test programs. So on behalf of everyone at Audio Precision and Gross Sound and Vibration, thank you so much for joining us today. If you have any questions that we couldn't get to or think of something after this webinar, feel free to contact us on our website, reach out to our tech support team, and they would be more than happy to discuss your applications with you. So thanks again, and stay safe.
All right, thank you, Paige. Goodbye, everyone.
Goodbye.